Okay, so welcome to this next video in which we are talking about the function of synaptotagmin, where we are concentrating on how it can bind to phosphatidylserine molecules within the phospholipid bilayer of the plasma membrane. And specifically, it's the C2a domain which binds to phosphatidylserine molecules. Okay, so what we're going to do is a very similar assay as we did for looking at whether synaptotagmin binds to syntaxin 1. So what we're going to do basically is we're going to take our synaptotagmin protein here and we're going to bind it to glutathione S transferase, okay? So here is our synaptotagmin protein here, and what we have done is we've bound it to this enzyme glutathione S transferase, which remember is this enzyme which adds glutathione molecules onto other proteins, or it might not even be other proteins, other biological molecules. For instance, glutathione S transferase enzymes, as we've denoted here by GST, glutathione S transferase. They are found a lot in the liver. You find many glutathione S transferase enzymes in the liver, and their role is to add glutathione molecules to toxic compounds, and basically to wield them untoxic now, to make them safe, to make them safe, basically, to make them unreactive. Okay, so we have added this glutathione S transferase enzyme onto our synaptotagmin, and the reason we're doing this is because glutathione S transferase, when it actually catalyzes this reaction and tries to add glutathione onto other chemical species, it forms a temporary bond with glutathione, and this bond is, when I say it's temporary, I mean it's a very stable bond. It's not like a really weak bond. It's a very stable bond. But the glutathione S transferase enzyme intends to add the glutathione onto something else and therefore break this bond. However, it's a strong bond, so the important thing for us is that glutathione S transferase is simply going to bind to glutathione. Okay, so now what we're going to do is we're going to go to the catalogue and we're going to buy tiny little beads, and I mean tiny little beads. So these are beads which are a few micrometers long, so they are tiny little beads. And you can buy these beads where they already have the glutathione molecule bound to them. So you can buy tiny little beads which have glutathione molecules bound to them. So GSH, this stands for glutathione, and you might wonder, well, how on earth does GSH stand for glutathione? Well, SH represents sulfur with a hydrogen bound to it, which is what's known as the thiol group. Glutathione's most important functional group is that it has this thiol group, basically, on its cysteine amino acid that's in the middle of it. Okay, so this G here stands for gluta, and then the SH is the thione bit, effectively. Right, so this glutathione, you can get it loaded on these beads. So you can buy these beads which are covered in glutathione molecules. Now, if we were to mix these beads with the synaptotagmin here, bound to the glutathione S transferase, then what would happen is the glutathione S transferase would bind to the glutathione on the beads, and that means that this entire structure here would all become linked, basically. So the bead would have the glutathione attached to it, the glutathione would have this glutathione S transferase attached to it, and the glutathione S transferase would have the synaptotagmin bound to it. So let me label everything up. So this is the glutathione S transferase here, this is synaptotagmin. So let me colour things in as well. So glutathione, we'll colour this in this turquoise colour here. Okay, glutathione S transferase, we've coloured that already in red, so we better stick to that convention. So this is red for glutathione S transferase. Okay, And finally, we'll have a pink colour for synaptotagmin over here. So this is synaptotagmin. Right, so now what were we actually trying to find out? We were trying to find out, does synaptotagmin bind to, does it bind to the phospholipid, phosphatidylserine? Okay, so we're only hypothesizing that it binds to it under the conditions of calcium. So we need to add calcium in, so we get our beads, we get our glutathione S-transferase with synaptotagmin bound to it, we add in calcium, so we've activated the C2A and the C2B portions now, and now we're going to get our phospholipids out. We need somehow to experiment with phospholipids. So what we get are liposomes. So here is a liposome. Okay, and specifically you get liposomes which have in them, as one of their constituents, maybe not their entire constituent, but at least partly, you have phosphatidylserine residues in here. Okay, so this little orange box now, rather than drawing the thing that I was drawing out before this, I've just drawn an orange box to represent all of that, basically. So this is a phosphatidylserine, which I've denoted PS. Now, the phosphatidylserine, if our hypothesis is correct, should bind to this this C2A domain here. So this is the C2A domain. Okay, then if we put this entire complex in a centrifuge, what's going to happen is, so if I get a centrifuge out, a centrifuge is just a machine which you can use to spin test tubes. So here's our test tube. The centrifuge is going to spin it, basically, and what will happen is these little beads, they will fall to the bottom and form a pellet. Now, if the phosphatidylserine really did bind to the synaptotagmin, then the liposome here with the phosphatidylserine in should be in that pellet. So how can we tell whether the liposome is in the pellet? Well, we can use a clever trick. What we can do is we can make this liposome out of phospholipids which have been tritiumated. So what we can use is tritiumated phospholipids, tritiumated or just tritiumated lipids. Okay, now what does this mean? Well, I need to tell you what tritium is. Tritium is a radioactive isotope of hydrogen, basically, which releases radiation. Okay, so the structure of tritium is that you have 3 nucleons, which is unusual for hydrogen. Hydrogen usually consists of a proton and an electron orbiting around it. In tritium, what you have is you have an electron with still 1 proton. You have to have 1 proton and 1 electron, otherwise it's not hydrogen, okay? But now, what you have is 2 neutrons here. So these blue things are neutrons. So, tritium is hydrogen. If you have 1 proton at your nucleus, then you are hydrogen. So what atomic element you are is determined by how many protons you have. The number of protons you have, the fancy name for that, is the atomic number. So the atomic number of tritium is indeed 1, which makes it hydrogen. However, what you can do is vary the number of neutrons. That doesn't change what element you are, but it does change your properties. So your mass number, okay, the mass number of an element means how many protons and neutrons are in there. So the mass number of tritium is 3. Okay, so this is hydrogen, so it often is denoted as 3H because its mass number is 3, or hydrogen 3 is also the other name that's used for it. But it's not the normal hydrogen. The normal hydrogen is something known as protium, which is just basically you have no neutrons. You have a single proton and then a single electron orbiting around it. So it would be H1 if you liked, 1H. Okay, and then there's another one in between which I think is called deuterium, which is the one where you have one proton and one neutron, so hydrogen 2. Okay, the point is, tritium hydrogen, or hydrogen 3, or 3H here, and indeed you will often hear people just describe this as 3H. They'll write it 3H, and then they'll put lipid there, well, 3H lipids, to denote that you have tritiumated them. Now, what does it mean? It means that when you construct these phospholipids, these R groups are going to have a huge number of hydrogens on them, most likely. Basically, you're going to use this tritium form of hydrogen instead of protium, basically. Okay, so you are going to make all of these phospholipids out of tritium rather than protium. And then you don't have to make absolutely every single hydrogen is tritium. You just need a good majority of them to be tritium. Then, tritium is going to release radiation. So, you can know exactly where these liposomes are just by pointing a Geiger counter at them, basically, which is something that measures radiation. Okay, so that gives you a way of telling whether the liposomes are in this pellet. Just take the pellet out, direct a Geiger counter at it, and see if it's emitting radiation, which indicates that the tritiumated lipids are in there, which indicates that the liposomes are in there. So, this is how we're going to perform this assay. We are going to get these beads with glutathione on. We're going to bind glutathione S-transferase to synaptotagmin. We're going to mix the beads and our glutathione S-transferase tagged synaptotagmin. They will bind together and form this complex. Now, we're then going to mix in liposomes with phosphatidylserine in. We're also going to put in calcium to activate the C2a and C2b domains of the synaptotagmin. We hypothesize that the C2a domain binds to phosphatidylserine, okay? And indeed, this assay will not quite show that it's the C2a domain that binds to phosphatidylserine. It will just show that synaptotagmin binds to phosphatidylserine. Okay, so continue on the story. If phosphatidylserine binds to synaptotagmin, then then this liposome will join this massive great complex. Then when you centrifuge it out, these beads are going to fall to the bottom, and it's going to bring all of this cargo, which is completely out of scale, understand. The bead is massive. These are microscopic. The bead is still tiny. You wouldn't be able to see this bead, but it's massive compared to these. Okay, smaller than a grain of sand, this is. It will fall to the bottom with all of its cargo. Okay, so we now need to understand, we need a way of seeing whether this liposome is in that pellet, okay, which would indicate that it had bound to the synaptotagmin. Okay, so that's why we tritiumate our lipids in this liposome, so that all we have to do is point a Geiger counter and see if it's emitting radiation. Bingo. So, what you find is that this works. The phospholipids do go into the pellet, indicating that synaptotagmin has bound to the phospholipids. Moreover, if you remove the phosphatidylserine from the liposome, i.e. you just make a liposome out of normal phospholipids, this does not happen. Okay, so you do not get the binding of synaptotagmin just to a normal phospholipid. It has to be phosphatidylserine. In addition, if you don't put in the calcium and don't activate the C2a domain, even if you've got phosphatidylserine here, it doesn't work. You don't get radiation in this pellet, i.e. the liposomes don't go into the pellet because they haven't bound to the synaptotagmin, because the synaptotagmin isn't activated. And let me just remind you of how synaptotagmin is going to be activated. Well, calcium is going to bind to it. So 3 calciums will bind to this C2a domain and 2 to the C2b domain. Okay, and what does this calcium do? It does not, I repeat, does not cause a conformational change. Instead, all it does is raises the electrical potential of both of these domains. So they become basically more positively charged, and that's why they can now interact with these phospholipids, because they have a negative, because the phospholipids then have a negative charge. So it does not cause conformational change. Okay, conformational, oh dear, change. Right, we'll call it there for this video, and we'll discuss another experiment that we're going to use to look into this in the next video. And basically the problem is going to be that we've done this assay which shows that the synaptotagmin does indeed bind to phosphatidylserine. The problem is, what we did is we mixed these all together, we left them alone for half an hour, and then the synaptotagmin did bind to the liposome. In neurons, they're not going to have half an hour to do this. They're going to need to do this in 200 microseconds. That's the speed at which you couple the calcium signal arriving to the release of neurotransmitter. So it needs to happen very, very quickly. So we need to show that this interaction between synaptotagmin and the phosphatidylserine here happens very quickly, and that's what we'll do in the next video.